Sam and the team of scientists are traveling from Moon to the Mars. But as soon as they were about to enter the Mars, they came to know that Mars is facing huge thunderstorms. And because of these thunderstorms, they will not be able to enter Mars that easily. They will have to increase their speed in order to enter the Mars environment. Now, let's see. Initially, they had planned to enter Mars with this speed, that is 3000 into log 1000 to the base 10. But now they will have to increase their speed by 1 by log 10 to the base 100. Now that the speed has to be increased, they will have to add this amount to this amount. Now, they will have to take this decision very quickly because the situation is getting worse with every second. So, Sam was tasked with calculating the final speed of the spacecraft. But this is a very complex sort of a equation where you have log 1000 to the base 10, which is multiplied by 3000, and then we have added it with a fraction, and the denominator of the fraction is log 10 to the base 100. Now Sam thought that if there was any technique by which he could actually interchange the bases simply, then his calculation would have been much easier, because then he would have the same base in both the parts of the equation. But that's not the case right now. Of course, he can apply the change of base theorem, but that will take a lot many steps to solve, and they don't have that much time. So he consulted one of the scientists on the spacecraft who suggested that he can usually use the law of reciprocals. Now, what is the law of reciprocal in logarithm? It says that if you have an expression like this where you have log a to the base b, and if you want to simply interchange the base and the argument, in that case you will have to reciprocate it. That is, you will have to write 1 by log b to the base a. So once you reciprocate it, so the argument and the base are interchanged. So let's see, is that really true? Can it really be done so easily without applying the change of base formula? Let's apply the change of base formula and see if this stands true. So in case of log a to the base b, now if we apply the change of base formula, we can write it as log a to the base a, because we want the argument to be the base. So log a to the base a by log b to the base a. This is the older base and this is the new base we want. So by applying the change of base, we were able to get this expression. So what is the change of base again? It is nothing but, if we have an expression like log x to the base a and we want to change the base of this expression, then for example, let's take the new base as b, then we can write this expression as log the new base b x by log a is the older base, that becomes the argument, and the new base is b. So we can write this with a new base b as this. So similarly, we have used here, we wanted a to be the base. That is why we chose a as the new base. So log of the argument, previous argument with the base a, and then log of the older base with new base a. That's how we got this particular expression. Now that we have got this particular expression, let's solve this. Now from the properties of logarithms, we know that whenever the base and the argument are same in a log, then the answer is always 1. So we have 1 by log b to the base a. So you see, log a to the base b when was used with the base change formula, that is the base was changed to a, we got 1 by log b to the base a. That is, this was interchanged with this and we got this. This is what we were trying to show in the reciprocal formula of logarithms. So this definitely stands true as the scientist had explained. So now let's apply this formula in our problem. So we had this as the previous speed and this as the additional speed they need to add to this particular speed. So in order to find the final speed, we need to add these two things. Now what we see is that here the base is 10 while here the base is 100. Now definitely we cannot simply add these two because they have different bases. So we need to bring 10 here and we need to bring 100 here. Then these both will have the same base. So if we apply this formula on this particular expression, then what do we find? So this remains unchanged, this part. So it's 3000 into log 1000 to the base 10 plus 1 by, now as soon as we interchange it becomes a reciprocal of this, so it will be 1 by log 100 will become the argument and 10 will become the base because we have reciprocated it. So now we have this expression. Now you know that if you want the denominator to come to the numerator, we'll again have to reciprocate it. That is, the denominator will become the numerator and numerator will become the denominator if it comes up. So we can write this as 3000 into log 1000 to the base 10 plus, now as log 100 to the base 10 will come up, then 1 will go down. So we know that anything by 1 can be simply written as this. Okay, so we can ignore the 1 here, so we can directly write log 100 to the base 10. Now does this look more simpler than this? Definitely it does. Now if we try to solve it, so we have log 1000 to the base 10. That means 10 will be multiplied 3 times. So the answer for this will be 3. And here 10 needs to be multiplied 2 times. So the answer for this will be 2. So we can write the simplified version as 3000 into 3 plus 2, isn't it? So finally we'll have 3000 into 3 is nothing but 9000 plus 2. So from here we'll get the answer as 9002. So this is the final speed with which they will have to enter the Mars environment, and only then they will be able to reach the surface. Now, as you know what the reciprocal formula is and how it can help you, let's see one more example. So here you see that we have 1 by log n to the base a plus 1 by log n to the base c. Now they both have different bases, and with different bases we cannot apply any particular operation. So what we can do is we can actually get something which is common as the base. Now here the argument in both the cases is same. So if we could bring the argument as the base, then the operations could be much simpler. Now, how do you actually bring the argument to the base? By applying the reciprocal formula, isn't it? So the reciprocal formula states that if log a to the base b is there, then if you want to bring a to the place of b and b to the place of a, you need to reciprocate it. That is 1 by log b to the base a. So we will reciprocate this. So we'll have n here. So we can write 1 by the reciprocal of this. So log. So we have n will come down here. So n will become the base and the argument will be a. So log a to the base n. Similarly, you have 1 by, again we'll reciprocate this too so that n comes here. So it will be log c will become the argument and n will become the base. Now again, we know that if we want to bring the denominator to the numerator, we will have to reciprocate it. That is, if we have 1 by x, then it will come as x at the top by 1. 1 can be ignored, so we can directly write x as the answer. So similarly here, we have 1 by log a to the base n. So you can write it as log a to the base n plus, similarly we have 1 by log c to the base n. So this will come up. So this can be directly written as log c to the base n. So by applying this reciprocal formula, you will be able to change this fraction terms into much simpler log terms with a common base. So now you know that. But what if this was not an expression but instead an equation? Then could you apply the same formula and solve it? Let's see. So what if log n to the base a plus 1 by log n to the base c is equal to 2 by log n to the base b? If you have such an expression, so can you prove something? What? Can you prove AC is equal to b square? Now that must be sounding confusing because everything is in log here, whatever you have seen, and now you need to solve something like this from this. Is that possible? Let's see. Let's first of all simplify it. Only then we'll be able to know how we can actually prove AC equal to b square. So the first part would be, again, you will notice that the arguments in all the three cases are same while the bases are different. So what we can do is, if we can bring the argument in the place of base and we can get the base in the place of argument, then we'll have the common base in all the three and then we'll be able to further simplify it. So if we apply the reciprocal formula, so we'll reciprocate it and we'll exchange their positions. So we can write this as 1 by, so this will become 1 by, again reciprocate it, so 1 by log a to the base n. Similarly 1 by log c to the base n. Similarly, this will be equal to 2 by 1 by log b to the base n. So you see how now we have all the three expressions with a common base. So now we know that if we want to bring the denominator to the numerator, then we will have to reciprocate it again. And now since we are dealing with all the ones, so we can ignore them and we can directly write it as log a to the base n plus log c to the base n is equal to, here we have a 2 already at the top, so that will keep its place because we cannot ignore a 2 in a multiplication. So 2 will be there and this will reciprocate and come at the top. So this will be log b to the base n. So this is the expression which we find by applying this reciprocal formula. Now, if we want to further resolve it, what can we do? We have this expression right now. Now, to further resolve it, we'll have to first think, can this particular part or maybe this particular part, can this be put into some sort of a law or a property of logarithm? Think for once. I think this particular part, which is the addition of two logs, is very similar to what we have seen in the product law. Let's see. The product law looks something like this, where we have log xy to the base b is equal to log x to the base b plus log y to the base b. Now, this part of the equation looks very similar to this part of the equation. And if this is so, then we can write this part as this part. So let's try to convert using this particular law of logarithm, that is the product law. So we have log a to the base n plus log c to the base n. So if we write it in the form of log xy to the base b, so this will become log ac to the base n, which is the common base. So using the product law, we have written this, and this will be equal to, we cannot apply product law here because we have just log b to the base n. So we write it as it is. So we get log b to the base n into 2. So this is the expression we have got. So by applying the product law, we found that log ac to the base n is equal to 2 log b to the base n. Now, is there any other property or law which can be applied to further simplify this? This particular part, as we have already simplified this, let's concentrate on this particular part. We have 2 log b to the base n. I think this looks very similar to the power law expression. Let's see how it is. So 2 log b to the base n and n log x to the base b. Do they look very similar? Actually, they are very similar expressions. So if this particular format can be written as this, that is, this can come as a power of this. So similarly, 2 can come here as a power of b. So we can write this expression using the power law of logarithm. We can write it as log ac to the base n is equal to log b square, that is 2 came here, to the base n. Now, what did we need to prove exactly? We need to prove that ac is equal to b square, isn't it? And now we have this particular expression. So once we have simplified this and we got this particular equation, so we have log to the base n on both the sides. Okay, so they are both common on both the sides and the expression is same, that is log ac to the base n is equal to log b square to the base n. So we can write this as ac is equal to b square, and that's what we wanted to prove. So this expression has helped us prove ac is equal to b square, and all this with the help of the reciprocal law or the reciprocal rule of logarithm, along with the product law and the power law of logarithm. So once you are familiar with the reciprocal law, the change of base, and various different laws of logarithm like product law, quotient law, and power law, you will be able to solve such complex equations very easily, and you can find from these equations, you can find simpler expressions like this. So isn't it really interesting? So I'd like you to try some more such problems and find out such interesting answers for the same using different laws and properties of logarithms.
Don't forget to subscribe to our channel. You can also register for free at deltastep.com to get all learning resources as per ICSE, CBSE, IB, Cambridge, or any other curriculum. Over 5,000 amazing lectures across maths, science, English, and social science. Our unique interactive video technology keeps you engaged, and our iDictionary feature allows you to quickly revise any concept. Master each topic at your own pace with our adaptive practice technology and 1 million plus questions. Get instant answers and detailed solutions. Be exam ready by taking unlimited mock tests, performance analysis along with actionable feedback, personal tutors to resolve your slightest of doubts. That's not all. You also get amazing prizes like PlayStations, iPads, watches, and many more, along with certificates through our Earn As You Learn program. So at deltastep.com, learning is not just fun and easy, it's rewarding too. So register for free now.